w.r.t. So this is what, for example, I would like to compute the way we did previously. Okay. So what will be our way of doing it? The way of doing it is going to be pretty much similar to what we did previously. So do you remember the two-dimensional Taylor series? So what will be the two-dimensional version of it? So the two-dimensional version of it is going to be this. So first of all, you're going to differentiate f with respect to the time. Let's differentiate t with respect to okay. So before doing it, I'm gonna do the same that okay, I have interval a to t and I split it into the mesh, and you know I'm making a sum I equal to 1 to n, and f of ti, okay, and w of ti minus f of ti minus 1 and w of ti minus 1. So, you know, it's really the telescopic summit. Okay? And on this increment, I'm going to apply the Taylor series. So, how does the Taylor series looks like in this case? Remember, if I write it explicitly, so f of tx, so recall f of tx minus f of fx naught, for example, s is some, you know, movement. You know, so s is some moment before time t, okay, and you want to make a computation, and so it's like you are starting from this point, sx naught, okay, and you want to make a Taylor expansion around this point, actually, okay. So this point is a deviation from this point, s and x naught, actually, okay. Then this is going to look like, okay, so it's playing another trick, which is okay. A big deal. F of tx minus f of fx plus f of fx minus f of fx minus f of fx naught. Okay, so what's a good thing about this now? What would be the good thing about this now? So it's like you are computing the increment, but here with respect to the time first, have the x same, and then here with respect to x naught, actually f of f yes,
time same x
naught. Okay. Anyway, so what would be this increment? So this increment is going to be, if you're gonna say expand it, so it's gonna be partial f by partial t. Okay. And okay, I mean, if I wish, I can write it directly, by the way. Okay, so partial f by partial t, and s plus rho t minus s. Let me write it and then maybe comment over it. X times t minus s plus partial f by partial x, and s x naught and x minus x naught plus 1/2 of partial 2f by partial x2. Okay, and s x naught plus lambda x minus x naught, okay, times x minus x naught square and x minus x naught square. Are we happy with it? So this increment is going to be that okay, differentiated with respect to the time on an instant between s and t, arbitrary instant between s and t. So rho is a number between 0 and 1. Okay. And differentiated with respect to x, okay, where at x naught, okay, so we have something here, yes, it's fine, and plus 1/2 differentiated second times with respect to x, and s and an instant between x and x naught. So this is like a remainder term, okay, times x minus x naught square, and the lambda is also between 0 and 1. The same strategy, just doing it with respect to both variables. So what I'm gonna do now, I'm gonna substitute, okay. So what I'm gonna do in this formula, I'm gonna substitute, s by ti minus 1 and x naught by, what? W of ti minus 1. And so t is going to be ti and x is going to be t. So
WTI.
So we're gonna do the same activity. So the outcome is going to be, so it's a simple Taylor expansion. So now this sum is going to turn out to be, in other words, this p w of t minus a w of a is going to turn out to be 3 sums actually, sum 1, sum 2 plus sum 3. Okay? So it's going to be 3 sums because this term turns out to be 3 terms actually. So we're going to have a 3 terms actually. New main, okay. ये C2 class assumption नहीं है यहाँ पर, so we don't have the C2 class assumption, but we have this actually. So partial f by partial t, partial f by partial x, and partial f by partial x2. So that's the. So we have only assumed the quantity of these 3 things actually. Okay. So it's a weaker condition than C2 being C2 class. That was going to be. So therefore, I'm not interested in the other terms. So what would be the first sum? So if I write it explicitly, so the first sum is going to be a sum that goes from I equal to 1 to n, okay, and partial f by partial, again, partial f by partial t of s plus, s is what is ti minus 1 plus rho ti, ti minus 1, right? ठीक है? Times ti, comma भी है क्या? Comma भी. What do you have? X, ठीक है? And ti minus 1. ठीक है? Question: if I take limit, and I'll do a better sense. Or if I want to ask to what this would converge in probability.
Riemann sense.
So it's going to be a Riemann integral. So what would be that Riemann integral? So this is going to converge from a to t. This partial f by partial t evaluated at s, w of s, okay, and the ds. That would be the first one actually. How about the second term?
Second term would be.
So the second sum is the sum that goes from I equal to 1 to n. And okay, so partial f. So this x is not really going to be x, is going to be w of ti actually. Yes, because I'm taking s naught, s as a ti minus 1 and t as ti, and x naught as w of ti minus 1 and
X is.
So that's what all this have to take care of it, and therefore I'm writing here. So I have partial f or partial x. Okay. Okay.
Very right.
So s is ti minus 1 right?
W comma W of ti minus 1.
W of ti minus 1 times
W of ti
W of
ti minus
ti minus
W of ti minus 1.
W of ti minus 1. So that is what is going to be.
Stochastic integral.
So this will go to what?
Stochastic integral.
Stochastic integral. By the way, I mean, if you remember here, I'm applying this result that if you want to compute, for example, you assume that, you know, I'm gonna state things more precisely in a minute, okay? But at the moment, I just want to give you a heuristic picture that what is going on, okay? I mean, if you remember, we said that if f is from L to a d square integrable and
In approximation lemma thing.
then you have this approximation lemma that says that, okay, if you want to do, this is the limit n goes to infinity, or, you know, that the maximum of the width of the mesh actually, okay? So let's take n goes to infinity, and this was in probability of what? Of a sum that goes from I equal to 1 to n, f evaluated at left end point multiplied by
The
increment of the Brownian motion. So in my previous result and this result, I'm applying this actually. So this is like my function evaluated at left hand point multiplied by the increment of Brownian motion. So therefore I'm saying that this guy will go to, you know, a to t f of s, w of s and tw of s. Is it making sense? Okay. So I'm applying this result. How about third sum now? Let's think about the third sum. So the sum 3 is a sum that goes from 1 to n, and I have partial to f by partial x2, okay, evaluated at s, that is ti minus 1, and x naught, that is w of ti minus 1, plus lambda times of, this is a tricky limit actually. We will really in its depth understand this tricky limit when we're going to do the proof of e to lambda. Okay? The proof of this e to lambda. So we'll see that it's not that much straightforward to take the limit actually. You have to work around the things. Okay? So at the moment I'm just saying that, okay, let's go on with it. So w of ti minus w of ti minus 1, okay, times w of ti minus w of ti minus 1 and square, okay? And intuitively, if you're going to take limit, this is going to be the integral from a to t, second order derivative with respect to x, and then evaluate this at s of w of s, and you know this would be a Riemann integral, okay? Because we know that, you know, in L2 omega sense, this is roughly ti minus 1, which, you know, if you take limit is going to be ds. Okay? Roughly. So
1 over 2, right?
Yes, obviously you're going to have 1 over 2 as well. But yes, you're going to have 1 over 2 as well. Is it making sense? Good. So this is really the proof by waving hands. We're going to get into the depth proof, but I would like to just give you a heuristic and then do some examples, and maybe in the end of the lecture we're gonna do the proof of it. Okay. So let's summarize what we have now. So if I want to write this in the form of the conclusion, so you have to keep in view that this is convergence in probability. Okay. But the convergence in probability we know implies almost sure convergence as well, but for subsequence activity, not in generic activity. So in a way, the identity that I'm going to write now is almost surely true. Okay? So what is that identity? That's really the slight generalization. Or this is sometimes called the simple lemma. So the previous one was simplest lemma. Okay, there's nothing like simplest lemma, but I wanted to discuss it explicitly. But this is called simple lemma. Okay, so here's a theorem that tells you. Let's call it simple lemma. So what you need here, obviously you need, if f is a function, that for that we need partial f by partial t, and partial f by partial x, and partial 2f by partial x2 are continuous, and f is obviously a function of time and x, okay, space, are continuous, okay, then f of t, w of t is going to be equal to f of a, w of a plus an integral from a to b, a to t. I mean, if you see in this sum, there are two Riemann integrals actually. So there are two Riemann integrals, you can put them together. Okay.
वहाँ पर probability sense क्यों आ रहा है इसमें?
कहाँ पर? Because that approximation lemma was the lemma in probabilistic sense. So that lemma allows us to use probabilistic sense. So, but you can show it in L2 omega, and then that applies, implies the convergence in probability. Anyway, so it's going to be what? So it's going to be partial f by partial t plus 1/2 partial 2f by partial x2, and okay, and this is evaluated at s w of s dw of s. Okay, so write it. So can you see that this argument goes here? Write it here. Plus a to t partial f by partial t evaluated as s w of s plus 1/2 partial 2f by partial x2 s w of s and ds. Okay, and plus 1/2 integral from a to t partial f by partial 2f by partial x2 evaluated at s, partial f by partial x, s w of s and dw of s. Alright? And this equality you have almost sure. So it's a p almost sure. Quality of ठीक है? Is it making sense? A little bit. What would be the differential form of it actually? So, it's a lot of pain to write all this stuff. Okay? So we're going to write a differential form of it. So what would be the differential form of it? The differential form of it is going to be that, okay, if you have f, if you have a function of time and w of t, so it's going to be equal to partial f by partial t plus 1/2 partial 2x by partial x2.
Sir, is there 1/2 in the last term?
होगी ना? नहीं होगी।
नहीं सर, वो वहाँ गई।
Plus partial f by partial x, and so that's a differential form of it, cryptic form of it. Okay? You have to keep in view, this doesn't have a meaning in calculus sense because there is no differential of, what do you call, okay, Brownian motion actually. Okay, but this differential has a meaning, so it's this integral meaning actually. Okay, we call this is written in a stronger form. It's a stronger form of differential. Okay? Alright. So this dt part, okay, is called the drift of this process, whatever this process is. So the drift of the process, and this the coefficient of dwt is called the diffusion of the process. Diffusion of the process. Which process? This process, f of dwt. Okay? And what is the advantage of this formula? The same advantage. Now you can compute differentials of the functions of Brownian motion, and hence you can also compute the integrals of the Brownian motion.
सर
So what
मेजर डिफरेंस क्या है दोनों में?
क्या होगा?
वो जो पहले हमने किया था
पहला was only f was a function of Brownian motion explicitly. Doesn't it depends on time? Okay. Direct. Now it depends on time. In other words, if
This
you
was
have
f from L2 since f from L2 to R.
from
The other, the simplest form of f was f from L2 to R. This is from 0 to time cross L2, right?
सर इज इट
yes,
Yes.
yes.
सर इज इट नेसेसरी कि वो जो क्वांटिटी है f w के ऊपर डिपेंड करेगी और wt के ऊपर है तो उसका अलग से t के ऊपर डिपेंड करना लाजमी
हो सकता है.
मतलब किसी और डायनामिक
Think about it that you have this kind of a function. Okay, so it's really what you call a function which doesn't depend on explicitly time. So imagine you have this kind of function. So you have f that is, say for example, t plus w square of t. So your previous formula wouldn't work actually.
No.
Because this is a function of time and function of Brownian motion. Okay, so that doesn't work. So
How would this over time?
f of t will be okay, so what would be the dynamics of such kind of a function? Okay, so you're going to say, okay, what is your ftx? Your ftx is really t plus x square. Okay? And then what the dynamics of this t plus w square of t is equal to what? This partial f by partial t. So if you're going to differentiate it, this will f is going to be 1 plus 1/2, and you differentiate it 2 times. So it's going to be 2. Okay, and dt plus.
Half t multiplied.
Half भी होगा. I have 1 here. Plus partial f by partial x is going to be
2x
2x. That means that 2w of t.
dw.
So this is really the dynamics of 2 dt plus 2 w of t dw of t. So that is that. ठीक है? This is what the differential of it is. But I'm again saying this has no meaning in this sense. It really has a meaning in integral sense actually. So this is just a way to convenient writing actually. Okay, you want to not write this detailed form of what we call lemma. Then this is a version of it. Right? Alright. So let's now generalize it slightly. So what would be, for example, from physical point of view, what would be the meaning of it? For now you are assuming that, now, your particle or whatever you have, okay, your stocks or some financial thing, anything that is random, okay, is depending on Brownian motion, okay. But now you want to know that what would be the dynamics, and by dynamics I mean differential. So these are the dynamics of this. So how this function of Brownian motion and time is going to evolve over the time. So this is going to be the evolve over the time, and this represents a trajectory. Okay, so we're going to learn that how to simulate such kind of trajectories. Are you getting the point? Now, you can do experiments. for example, classical mechanics things. It's not going to be that easy as I'm saying, but you can play with it. So take your deterministic equation, okay, that represents something, okay, that gives you the evolution of some particle or maybe evolution of some something actually, okay, and you want to assume that no, I know that when, for example, a ball is making a parabolic trajectory, it's not really a purely parabolic trajectory. No, it's a wiggly trajectory actually, because there are multiple forces that are acting on what do you call that ball that. And in deterministic sense, you just ignore them all. And now you say that no, see them in originality. Assume that the particle is your ball is making a parabolic trajectory. Okay, and now you want to know something about this ball that makes a parabolic trajectory. Energy and velocity and everything. But all these things are going to depend on the trajectory. I mean, you did the entire course on what do you call classical mechanics. So what you did? So you develop an equation of motion and try to find displacement. And once you have displacement, you can find rest of the quantities from it actually. But now what we are saying that let's assume that that displacement and that thing is a random thing actually. So you have some noise added into it. And you want to know some quantity, okay? You want to know some evolution of some quantity, okay? Over the time, the question is that what will be its dynamics? The answer is that you have this lemma telling you that how it will evolve over the time. Okay?
तो फिर हम noise को कैसे represent करेंगे? यहाँ पे तो
w of t is a Brownian
वो
motion.
given होगा हमें.
Yes, I mean, you are assume actually that. So okay. So you have to fundamentally assume that. Okay. So for example, when you are doing things in classical mechanics, you say that things are moving under the influence of the gravity. So you have this assumption actually, and then you try to dig out the equation. So you have fundamental assumptions that things are interacting with each other under these fundamental forces actually. Okay. So now you're going to say that okay. I have a particle but it's moving randomly. Okay, how it is moving, let's assume that it's moving, its trajectory is same as the trajectory of Brownian motion. Maybe as some function of Brownian motion. Okay? And then, if you think that, the Brownian motion is not a good approximation, then you can change the noise and you can try to fit in the more, suitable noise. Okay? But the calculus would be almost similar actually. You have to develop an Ito lemma that can tell you the dynamics of the function of your interested quantity. Okay. So this is really the beginning of it. So finance people say that assume that the stock is following geometric Brownian motion. Okay, it follows some differential equation actually. And then you say, okay, I have an investment that depends on this stock. And I want to know, for example, dynamics of my gains actually. The gains depends on the dynamics of the stocks actually. So the question is that what would be the dynamics of those gains? So you can compute those dynamics. Okay? And now what we're going to do, we're going to even more generalize this actually. So the general Ito lemma. Okay? General Ito lemma. This is an interesting case.
टाइम को आर्बिट्ररी करेंगे कोई वेरिएबल
और हम कहेंगे कि imagine